In the last video we saw that the motion of a pendulum bob for small angles theta is simple harmonic. That means the acceleration of it in the x direction, that's along the curve, is proportional to x. X could be positive or negative depending on whether the bob is to the right of its equilibrium position or to the left of its equilibrium position. We also saw that the period, which we know to be 2 pi over omega, is 2 pi times root L over G, where L is the length of the pendulum bob and G is the acceleration due to gravity. So the period does not depend on the mass. M does not come into this formula. So it doesn't matter what value of M we have here, the period or the time taken for the bob to complete one oscillation is the same. Depends on L and G only. Now what is the period? Well, suppose the bob is in its position here, then the period will be the time taken for it to go all the way through its equilibrium position, reach its maximum displacement or amplitude, come back again through the equilibrium position, reach its maximum displacement, and then come back to this position. So the time taken for that is 2 pi times root L over G. We can see that if L increases, we increase L up here, then the period will increase, T will increase. The period is referred to as capital T. Another thing is G. If we could change the acceleration due to gravity, we can affect the period of the pendulum bob. We can see that if G increases, then the period will actually decrease. If we increase the denominator of this fraction, we decrease the entire quantity. We decrease the period. So we will see a simulation where we can play around with these values. We can play around with the length of the pendulum and the acceleration due to gravity. Well, of course, we can't just play around with Earth's gravity, but we can imagine G for different planets, where the force of gravity varies. Here we have a pendulum bob whose mass is 1 kilogram and the length is 2 meters. Friction is turned off. We will only be dealing with the case of no friction. We can set this bob in motion, obviously, by extending it by so much. Let's extend it by about 8 degrees. Of course, we know that the bob will undergo simple harmonic motion if the angle is small. If it's less than 10 degrees especially, we get a very good approximation to simple harmonic motion. So let's say it's 9 degrees. Now we can show the velocity and the acceleration. Let's see the velocity first. No surprise there. We can see the velocity vector dropping to 0 when the particle reaches either ends of its motion. The velocity is a maximum when it passes through the equilibrium position. Let's look at the acceleration. Now, the acceleration basically gives us the resultant force on this mass. The acceleration is not always along the path of the mass. You can see sometimes it's pointing towards the center. So the acceleration is just the resultant force divided by the mass. So the resultant force will be in the same direction as the acceleration. So by looking at this, we can also see the resultant force on the mass. In the last video, we were looking at the x component of this acceleration. That is the component along the circular path of the particle. Let's increase the mass. That has no effect on the acceleration. It has no effect on the periodic time either. That's the time taken for one oscillation. Let's see the period. we see the period is 2.84 seconds. If we change the mass, the period will remain the same. As we saw before, the period doesn't depend on the mass. So the time taken is still 2.84. Now we will increase L. As we saw before, if we increase L, we increase the period T. So let's increase L. So I set it here to 2.5 meters, and let's look at the period. See, it's gone up to 3.17. Let's decrease the length. As we saw before, if we decrease the length, if L goes down, then T should go down. The period should go down. So let's look at the period of this motion. See, now it's only 1.42. We saw that if G goes up, then the period goes down. If we increase the denominator, the period goes down. So let's increase the value of G. Now to do that, we could look at the acceleration due to gravity on Jupiter, which is a much more massive planet than Earth, which means that its value of G is a lot larger. We see the period is less, as expected. So the time taken for one oscillation is a lot less, it's moving faster. Let's decrease G back to Earth's value again. And if we decrease G, the period goes up. So now it's gone back up to 1.42. So decreasing G will increase the period, of course. Make this number smaller, make the denominator smaller, T gets bigger. Let's make G even smaller again. Let's look at the acceleration due to gravity for the Moon. So the period is even greater now. So now it's 3.48. As I said before, the period doesn't depend on the mass. M doesn't come into this formula for the period. So one way to see that, a nice way to see it, is to look at a second pendulum with a different mass. A second pendulum with the same length but a different mass. So make the length, say 2 meters. But let's change the mass of the second pendulum. The mass of the blue pendulum is 0.3. So let's make the mass of the red pendulum 2 kilograms. It's much heavier. Now let's set both pendulums in motion. So let's extend this to, say, small angle, keep it less than 10. And do the same with this. The same amplitude, 9 degrees. Or angular amplitude of 9 degrees. Let's start the motion. We see that the period for both of them is the same. They're moving together. So the mass doesn't affect the period. Another thing that we could do is look at the energy of this pendulum. So here's an energy chart showing the kinetic energy and the potential energy. The thermal energy is 0 because friction is set to 0. So we've no heat energy. This bar here is the total energy. The height of this third bar is always a constant. Let's just increase the potential energy by increasing the mass. Potential energy is mgh. Depends on the mass or the weight and the height above the Earth's surface or some reference level. Of course, increasing the mass also increases the kinetic energy, because kinetic energy is a half mv squared. So we double the mass, we double the kinetic energy. But the total energy remains constant. We can see how kinetic energy is being converted into potential energy and vice versa over and over. No friction is acting, so this pendulum will oscillate forever. Let's see the velocity. You can see when the velocity is high, the kinetic energy is high. Let's just slow this down. See, when the speed is 0, the kinetic energy is 0. I'll slow it down further. So the kinetic energy drops to 0 when the speed is 0. Kinetic energy reaches a max, and the speed reaches a max when the mass passes through its equilibrium position. The potential energy is actually at a max when the particle is at either end of its motion, and it drops to 0 when the particle passes through the equilibrium position. So the reference level for the potential energy is passing through the equilibrium position, actually. It's not just the distance above the Earth. Although we can set that distance to be anything we like when we consider the potential energy, but it's probably easier to set the reference level at the equilibrium position. So the potential energy drops to 0 here. So I think this is a very nice animation. It's worth playing with. You have the link there